Suddenly, a Dalek walks into my classroom.
So there's this hunter, and he wants to shoot a magnet for some reason.
Welcome back. This week's lesson is going to look at charges moving through electric fields. It's quite a nice combination of applying all the different things we've learned so far. So first of all, we're going to take the simplest case. We're going to say our charge is going to move parallel to the electric field. What this means is all the force is going to be applied in the same direction that it's moving. So we have in this case an electron that is going to start at the negative plate. The field lines are shown from right to left because they always go from positive to negative, and our particle is going to experience a force in the opposite direction. The field lines are defined for the force applied to positive charges, if you remember back to our first lesson. Another way of thinking about this is our negative electron is going to lose some electrostatic potential energy when it moves from here, where it really doesn't want to be, it's next to the negative plate, and moves closer to the positive plate where it does want to be. So it's going to lose potential energy, and therefore it will gain kinetic energy. And that's the basis of the mathematics here. So we're going to make life a little bit easier and assume it is completely stationary to begin with. If your speed is very low, that's probably a reasonable assumption. It's reasonable because the speed you tend to leave at is very, very high indeed. But if it wasn't true, what you would need to do is first work out the energy it has, calculate the energy it gains, and then add the two energies together before converting from kinetic energy into velocity. The mistake some people sometimes make is to try and add up the speeds, but that doesn't work. In any case, looking at the simpler case here, the kinetic energy will be equal to the potential energy lost. So half mv squared is equal to charge multiplied by the potential difference between the plates, or voltage for short. Rearranging v squared, that's speed squared, will equal to 2qv divided by the mass. And you can take the square root if you particularly like. So this tells us the speed will increase depending upon some fixed things, the charge on the particle, the mass on the particle, and the voltage across the two plates. So a higher applied voltage results in a higher speed. So you can make your electron go as fast as you like as long as you have enough voltage. There is a bit of a problem here, and the problem is there is a speed limit. The speed of light is the maximum speed anything can ever go, and according to this, with a big enough voltage, you could exceed that. In simple terms, this equation is limited. It's an approximation that ignores the effects of relativity, and as a rule of thumb, if you go over 10% the speed of light, you probably ought to start taking that into account. It also turns out it's relatively easy to get into that territory. So, for example, if I take the charge on an electron and the mass of an electron and a voltage of, let's say, 2000, it turns out we end up pretty darn close. So here's our equation, we substitute in the numbers, and then we can solve that. The calculator says it's this value, don't forget to take the square root, and now we're at almost 90% of the speed of light, apparently. In this case, that wouldn't really be a fair calculation to go with, and we would need to do something better, but this shows you just how easy it is to get to very, very high speeds. In exams, I doubt you'll be asked questions with voltages as high as this, but it's just to demonstrate the effect. If you experiment with these things in the lab, 2000 volts really isn't that hard to get. The mains is already 240, and you just need a 10-to-1 transformer to get up to 2000. And already you have particles that are moving so fast that you've basically made a constant stream of beta radiation, so you have to be a bit careful. Another teaching point is that this equation is not given to you in the exam, nor should you expect equations like that to be given to you. At National 5 and higher level, you pretty much had an existing equation for most questions. There weren't many times when you had to combine them and process multiple things coming together. But at advanced higher, that's actually quite typical. It used to be that there was a whole set of derivations you were required to memorize, as well as you needed the problem-solving skills to handle new and unique situations you hadn't seen before. In my notes, like most teachers, I will try and give you an experience of a whole range of these things to prepare you as best I can, but fundamentally, you are expected to be able to do exactly what I've just done here. You take pieces that you know, you analyze the situation to see how they're related, and then you apply the logic to solve the problem. That might sound tricky, but it's something you're going to have to get used to. So how might we use this effect? Well, this is an animation that shows a more realistic situation for a particle accelerator. Particle accelerators are used in science for studying particles, like say CERN for example, but they're also used in industry to make certain chemicals. If you want to make isotopes, one thing you can do is take an existing material and bombard it with protons. That's what's happening here. We have a positive source of protons that's releasing these, and it is being accelerated as it moves from one coil to the next. This results in it gaining more and more and more speed. Now you might say, well, before I said just use a big enough voltage and you can do whatever you like. Well, that's true, but there are limits to that. It is quite difficult to just take anything really and increase it more and more and more and more. So this little trick allows you to use the biggest voltage you've got, but you can use it over and over again. That's quite nice. So what we're trying to do is always have the positive plate behind our particle and a negative one in front of it. And it turns out you can't do that with a DC current. If, for example, you had time frozen here and the first coil was always negative, well, sure, at the start our particle will be attracted into it and it will accelerate, but then when it tries to leave this section, it will be pulled back. It will be slowed down again, and that really won't help you. What we need to do is use our alternating voltage here to basically flip the plates or flip the coils just exactly at the right time. And we know the starting speed of our particles are pretty much zero here, so this will be a consistent, reliable effect, which means you can arrange the physical geometry and the size of the tubes to basically balance out for the fact that these particles are going to get faster and faster as they go along. So for the first bit, our particle has the negative plate in front of it, positive behind, and then when we're inside it, well, that's fine, keeps going, but as soon as we're past the halfway point, we swap things around, so the first coil becomes positive and the second one is negative. That attracts us further and further, speeding up more and more, and then we'd have a problem, but again, we swap it back over, and that works just fine. CERN uses a whole series of coils like this over and over and over again, all the way around their tunnels, to accelerate things over and over and over again. They approach very, very close to the speed of light when they collide their particles. To properly do this at very, very big scales, you can't really just do it in one straight line. Most industrial applications will do just that. They'll have a big tunnel that's really quite big. They'll sort of build the whole building around it, but there are limits. If you want to go really, really big, you're forced to do this in a circle and loop back on yourself. And if you want to do that, you also need something to keep these particles from crashing into the sides of the wall. And it turns out they use basically other coils and magnetic effects to do that. We'll come back to that in the next topic, but for now, let's just look at accelerating them. The next application I'd like to share with you is a cathode ray tube. This is the science behind the old-fashioned TVs that I'm sure you've maybe seen in films and things. Sadly, they're not around too much anymore. This used to be a major piece of sort of study in context as part of the old standard grade, but the technology has moved on quite a lot, and these very, very big, bulky devices just aren't really used anywhere anymore. But the basic idea is you have a screen at the front, and the screen is coated with a paint that glows when electrons strike it. So electrons crash into it, and that causes the paint to give out light. If you have a pair of coils, one pair above and below and one pair to the left and right, you can direct this beam to scan its way across the whole screen, lighting up one pixel after the other. By blocking the electrons partially or wholly, you can turn the brightness of the different spots to different amounts, and that's enough to produce a black and white image. This whole cycle, this whole frame needs to be painted 30 times a second. So our electron gun scans across really quite quickly with a pair of coils that are at both sides. The simple thing, which is quite nice though, is it doesn't matter which picture you're showing. The pattern for scanning this gun is always the same. And one type of scan pattern is this one here, where you go left to right and then jump back to the start, left to right, and so on. And all this happens every 30 seconds. And by setting the electric fields with these coils based on voltages, you can control this pattern. And this is roughly what happens. You can see here with this particular TV, it's quite a big one, there's one coil on top and there'll be another one at the side. One of the reasons these things need to be so bulky is because, again, all the air inside has to be evacuated. So you get this very, very thick tube, this very thick piece of glass. Also makes it quite heavy. And then our electron beam can only be deflected so far. There's a certain angle limitation. So if you want to have a nice big screen, well, the gun has to start quite far away, which means you end up with this big box effect. Quite big, bulky things. The electronics required for this pattern are actually quite simple. We want to go from left to right every so often at a certain frequency. Here we have 16 pixels by 16 rows, and so you can see here that for each row our electrical signal is going to go from all the way negative all the way positive. And that does this red line here. To control which row we're looking at, we have this signal for the Y direction, and basically it's just a sort of step function, and to begin with it's at the highest value, which means you're on this row. The next one is slightly less as you go along. This is only half the pattern, the second half would be nice and negative. This quite simple, predictable pattern is set up, and then really you just have to worry about turning it off and on your electrons. That's quite nice. The other application that's actually really still relevant today is an oscilloscope. An oscilloscope is pretty much the same technology, only you don't have a program controlling the coils, you connect whatever electrical signal you're trying to study to it. And this is a sort of part of the overall oscilloscope here. This is the real part, if you like. You have your screen that has the same fluorescent paint, but there's also a grid. The grid allows you to take exact measurements. You have inside an electron gun, which produces a spot in the center, that's all fine, but the coils that are around this can be directly connected to. You can see the connections going in here, and there's sort of little ports at the front here for plugging things into it. One of the reasons that this piece of equipment is so very nice is because it doesn't have any complex electronics and it doesn't have any software at all. You never need to update your oscilloscope, it is a physical device. The signal directly controls the electron beam, and as a result of that you can be sure that there isn't any subtle complicated effect getting in the way of your measurements. And that's the most important thing when you're doing science or high-level engineering. You want to be absolutely certain that your measuring tool is telling you exactly what the thing really is, and not just some random guess that a programmer somewhere built into the working. A common thing people aren't aware of, for example, is if you use a voltmeter to measure an AC voltage, it typically only works if your frequency of that signal is pretty close to the mains voltage frequency. If you try and plug it into other things, it just doesn't work at all. The electronics and the software involved has certain assumptions built into it, and that's a problem. You can get apps that function as oscilloscopes, and they are nice and flashy and all the rest of it, but there's always that problem. If you really were doing something where you had a £1 million project that you were working on for 2 or 3 years, you really don't want the app that you're relying on to suddenly update halfway through it. Because if something happens to your data that changes things halfway through, you want to be sure it's a real effect and not just a random update. So giving control of your tools to random people around the world isn't a very good thing. In everyday terms though, it's quite nice to get free software updates. Anyway, back to some calculations. Well, we said before we were going to move parallel to the field, but what happens if we move perpendicular to it? Well, in this case, our electron's going to travel along, but the field lines are pointing down the way, which means our electron will experience a force up the way. And as a result, there'll be an acceleration, and as a result, there will be a deflection of that beam. What determines that? Well, first of all, is how long you're going to spend in this field, how much time, and that just depends upon the starting speed of our electron. See the first part to figure out how you'd figure that out, and the length of the plate, a physical dimension. We're kind of ignoring the edge effects here, they're just quite inconvenient. They're a small effect, so we can ignore them. And you can work out that time here. You can say the time in the field is going to be equal to the length of it divided by the speed. This is sort of like the opposite way round of projectile motion. So for higher course, you have the projectiles where the vertical part determines how much time you're in the air, and the horizontal speed determines how far you're going to get. Whereas here, it's the horizontal motion that determines how long you're in the field, and it's the vertical force that's going to determine how much deflection you get. So vertically, we're going to have a look at the forces, and it says here that F equals ma, sure, so acceleration is force per mass, and then you get to ask, well, what's the force going to be? The force is going to be based on two things. The first is the electrostatic repulsion up the way, and then the weight is going to pull us down the way. Here it says the weight is negligible. You might say that seems unlikely. Weight's normally quite an important thing, but at the atomic scale or the microscopic scale even, weight is completely of no interest whatsoever. Even if you're doing a super sophisticated simulation on the world's best supercomputer, it's just not worth the effort to even type the code to simulate the weight of different particles. The size of those forces is something like 10 orders of magnitude smaller than anything else, so it has no effect whatsoever. It's a good rule of thumb. In the very big scale, like say anything that you or I can pick up, things like the electrostatic forces make no difference. But at the very small scale, it's the other way around. So here we have our acceleration. It's the electrostatic force divided by mass, and using the definition of electric field as force per charge, we can swap that in here. So the force is equal to the electric field multiplied by the charge if you bring it up. And that's this equation here. You have the option of also saying that the electric field is determined by the voltage and the separation of the plates. That's the sort of distance up and down the way here. You do have to be a little bit careful. This distance here is just a generic distance for distance equals speed times time, whereas this d is a specific one for this context. So as I said, you could do that, but I'm not going to here. The big story is that overall we have this description here. This is the equation of motion from higher. It describes a parabolic curve, which is what we've got here. So S equals ut plus half at squared is true for every single object ever, including our nice little electron. But at higher, A was always a certain number. But here you have to calculate it. It's a certain equation. And time also is an equation. So you put both of these things into here and you should be able to work it out. Typically, the starting vertical speed is going to be 0. That's true any time you have motion perpendicular to the field lines. If you were to come in at a certain angle though, maybe you'd have to decompose that vector to work out the starting vertical speed and take that into account as well. So let's look at a word example. In this one, an ink printer has droplets of this mass which acquire this particular charge here. They basically fall through a mesh and pick up the charge as they go along. We're told that it enters the field between two plates at this particular speed, and we're told the length of the plate as well as the electric field between them. We're asked to calculate the deflection shown in this diagram. Ultimately, we use the equation of motion, but first we have to find the acceleration. We know acceleration is force per mass. We know the force is going to be electric field times charge, and we can put all those numbers in and end up with this number here. It's quite a big number, but that's actually to be expected for a tiny little ink droplet. We can work out the time between the plates with distance over speed, and putting those numbers in, and we get, roughly speaking, 1 millisecond. Quite reasonable, because you would expect to produce lots and lots of droplets every second, and that kind of makes sense. Putting both numbers in, we end up with a value of 6.4 times 10 to the minus 4, or kind of half a millimeter. Quite a reasonable deflection for this type of context, I would say. For the next one, it just says, find the displacement produced by this apparatus. And you get various pieces of information from the diagram. And if you've never seen this before, it might sort of throw you off a little bit. But it's actually a reasonably standard type setup for investigating fields like this. So what you might see is a diagram like this, where it says you have a heater, and then there's an electron gun arrangement which fires a stream of particles, and there are two plates where you can deflect them. This sort of setup here shows you the different parts. You have this thing that looks a bit like a light bulb. That's because all the gas has to be evacuated out if the electrons are not going to react with it. And you have one power supply for the heating part, another power supply for the electron gun, and a third one that can power these electric field plates. There's also sort of coils of wire that can go on this way for producing magnetic fields, but that's part of a different topic. The nice thing about this is you have a little scale on there, so you can change the voltage and you can measure how much deflection you get. And in theory at least, you can demonstrate all of these different effects. I have used these before. They are very, very expensive though, so very few people have them. This piece alone is about £800, and all of these other pieces are expensive too. But the nice thing is you can see the deflection. It's very rare to actually go and do exact measurements though, but if you really wanted to make that into an advanced tower investigation, it's at least possible. So you might come across these though, even though the equipment is rare, there aren't that many contexts the exam can be set around, and physics questions always come in a context, so they do come up quite a bit. Here we're going to find our acceleration, and it's force per mass again, and again force is going to be the electric field multiplied by the charge, and in this case I've kind of skipped an extra step in there, and I've said electric field is the voltage divided by the distance. That's for a uniform electric field between any two parallel plates. Put all the numbers in, out comes this value here. Secondly, to work out the time, well, it's going to be a certain distance, 80 millimeters, divided by a certain speed, which is given over here. It's a very, very big speed, so we have a very small time come out. Putting all of these things together, and we get a displacement of about 12 millimeters or 1 centimeter or so, which is quite typical for these screens. You can see here it's, this would be 25 millimeters, so it's about half of the way along the scale. That seems reasonable to me as well. Now I'd like to look at some of the advances we've had in science based on this type of work. In 1909, these guys, Geiger and Marsden, they did some work on the behest of this guy, Ernest Rutherford, and that led to an improvement in our understanding on how atoms are structured. You see, in the time, the Thomson model was the leading theory. It basically said that atoms were not just complete spheres, but they were basically spheres with little pieces inside. Those pieces were known as electrons. But Rutherford's work, he did the maths and the other guys did the practical work, showed that that's not really the case. If you take an alpha source and you use it to bombard a gold foil with the particles, then what the Thomson model predicts, according to Rutherford's maths, is that the particles should go straight through. Maybe be a little bit spread out, slightly wider out here. But what the experimentalists discovered was that actually you get this effect. Sure, most of it does go straight through, but it's not exactly spread out evenly. You get some of them at all sorts of angles, and the ones that are deflected at very, very high angles, like this one here for example, that's the result that Rutherford used to show that there was something wrong with Thomson's model. You see, mathematically, to get that severe a deviation, you have to have a very large concentration of charge. You have to basically almost hit the nucleus. And that led to us accepting that the nucleus exists, the positive charges are all centralized together in a nucleus, and you can work out other things from there. This is a picture of a replica of their very equipment. You can see a microscope for staring at things for a detector, and the little foil would go in here. We can do other things as well. The basic analysis, which I can share with you, is that if you want to figure out how the alpha particles can approach the nucleus, we can figure it out based on energy. To begin with, however you arrange it, the particles are going to have a certain kinetic energy. It's not like it's a spaceship with a little thruster here. Once they're launched or thrown, all the energy they have is what they start with, and that has to be used to overcome the electrostatic repulsion. So we know an expression for the energy that is required to get to a certain distance next to whatever charge we're talking about. And by equating the two of them here, we're basically saying we're aimed straight at the nucleus, how close are we going to get? And this allows us to either calculate what the closest approach is going to be, or we can even calculate how fast we might have to start them going in order to make them touch. And that was seen as being extra important for basically starting a fusion reaction. That was the big sort of interest at the time. But here's a worked example. We're told an alpha particle approaches the nucleus with a certain speed, that value there. The distance of the closest approach is this number. And then we're told, quite strangely maybe, identify what the nucleus is. At advanced higher, it's quite common for people to read a question and to feel completely floored by it. They might have read the notes or followed the examples from the teacher, and they thought all was well, yep, it made sense when the teacher said it. They then sit down in the exam and they get completely blindsided. Often students interpret that to mean that the questions on the exam are significantly harder than the ones that they've been practicing with. But in reality, what's happening is you just don't have someone explaining the basic steps to you. You need to be able to focus on what you do know and apply it, and that's quite tricky. It takes a bit of practice. But here in this case, the only thing you can do is deal with energy. You know about kinetic energy, you know what the expression for potential energy is as well, and so we can equate the two of them. Basically, being aware of this first step is the big burden. And we know the starting speed, we know the mass of an alpha particle, this is a constant, we know the charge on an alpha particle, and we know the closest approach. So we can solve this to find the charge on that nucleus. Once we know the charge, we basically know the number of protons, and from that we can identify at least the atomic number of that nucleus. Can't tell you much about the mass number. And we can solve all this, and how I've chosen to frame this is for the charge I've substituted n times 1.6 times 10 to the minus 19. So n is a number of protons, and this is the charge per proton. By putting that into my calculation, it allows me to solve it a bit more easily. And long story short, a whole chain of numbers go in, and you can do the sum as best you can, and you end up with a value that comes out at about 80. Sometimes when we're rounding, we maybe forget what it's all about. At higher level, you rounded based on the number of sig figs in the question. At advanced higher level, sometimes you might be given things like reading uncertainties and you really have to process it carefully. That's the better approach. But here, the rounding is determined by the physics. We're saying that we're finding the number of protons. You can't end up with an answer of something like 80.5 protons. It's a bit like saying, how many people did you have at your house last night? And you say, oh, it was 4.5. You can't just chop things into pieces. So here we know the answer is either going to be 80 or 81. And yes, it's a fairly sort of nasty example to try and round this. Obviously there's some uncertainty in all these sort of values that we've put in here, but the only reasonable thing is to round it all the way up to 81 and say that's how many protons there were. In this case, that's a thallium nucleus. Finally, the last thing to discuss is the work of Robert Millikan. In his time, he was working when it was already known what the charge to mass ratio of an electron was. J.J. Thomson had discovered the electron, and he had figured out not either the charge or the mass, but their basically multiplied ratio together. As soon as someone could figure out either one of them, we would then know both of them and be able to do all the sums that you now enjoy. And Millikan was a very, very good practical focused man, and he was able to come up with a setup that allowed us to very, very carefully measure these things. The basic idea is that he would first work out the mass of an oil droplet by watching it fall and finding its terminal velocity. This basically was done in a big chamber. It looks something like this. So he would spray a bunch of little oil particles into a box, and there was a hole in the top box, and some of them would fall through. They were then irradiated with radiation that caused them to gain a charge. They were now charged particles of a very small size, and what he was able to do is stare at them with a microscope against a little scale at the back, and you could measure how fast they were going. This was required because they were very, very, very small droplets indeed. Because they have a charge, what you can then do in part 2 of the process is you can work out how big that charge is by finding the voltage required to suspend it. You see, there is weight pulling the droplet down, and when you have the second part, there is an electrostatic force pushing it back up. And that's the basis of his experiment. Now, I'm sure many people try to do similar things, but Millikan was so successful because he was incredibly careful and really, really meticulous in making sure everything was as good as it could be. For example, the entire apparatus was surrounded in a bath of motor oil in order to keep the temperature exactly the same. For the first part, I don't really want to go into the details, but there are a few forces to bear in mind. The first of them is that the particle has weight pulling it down, and when it's at terminal velocity, there's two other forces you need to take into account. The first is Stokes' law, which is to do with air friction, and it's basically this equation here. It was figured out by looking at mathematical dimensional analysis and measuring values. So it's 6 pi multiplied by the radius of the oil drop, multiplied by the speed it's falling, and then finally multiplied by this term here, this mu, which is sometimes written as a Greek n. that is the value of the viscosity of the fluid you're falling through. In this case, it was air. So that was one part of it. The second part is you need to know about Archimedes' principle. That used to be part of the higher, but no longer is, and it basically is the science of floating. If you are in a fluid, like air or water, then there will be an overall force pushing you up the way, and that's based on basically how much air you're pushing out of the way just by being there. So it depends upon the total mass, which is going to be the density of the air multiplied by the volume of your droplet, and then times by little g. If you combine all three of these things together, so the drag, the buoyancy, and weight, and do a little bit of algebra, you end up with this equation here. This is Stokes' law for terminal velocity, and it depends upon the density of the oil as well as the density of the air. I encourage you to have a look at that if you're interested in it. It often makes quite a good advanced higher project, but for now, the only thing we really need to know is that the speed of the object is directly related to the radius. You have to know about the properties of air, both its density and its viscosity. You need to know little g, and finally you need to know how dense your oil is. But all of these values are constants in the experiment. The only thing they're really interested in is speed linking to the radius squared of the droplet. Anyway, that's part one. You've figured out how big your droplet is, and then what they want to do is basically mess around with the electric field strength by changing the voltage. When they did this, they did it with thousands of different droplets over and over and over again, and when they were doing it particularly well, they would choose a single droplet and they would suspend it with the electric field, allow it to fall, measure some things, and then they would increase the field to lift it back up, and they would do it over and over and over again for different charges with the same droplet. And that allowed them to build up a database of thousands of different charge readings. In part two, when you're balancing the oil droplet with the electric field, we know that the weight of it is going to be supported by that field. The force from the electric field is charge times the electric field strength, which we know will be volts divided by the distance, and we can work all this out here. So the charge will depend upon the mass of the droplet, which just depends upon its density and its radius, little g, separation between the plates, and how big the applied voltage is. These are some pictures from Millikan's real work back in 1917. This is the basic tank. This is where it all happened. This is his little spray for the oil. Here's the microscope, and I think this is the radioactive source here. The whole setup was surrounded by other pieces of equipment like this, and you can see here the schematic for where the basin was suspended in a reservoir of oil that was continually pumped through in order to very, very carefully maintain that temperature. There was a small mistake in his work. We think it was related to the value of the density of air, but Millikan was very, very precise in what he managed to achieve. Now his analysis was quite amazing at the time. You see, he measured a bunch of charge on a bunch of different drops, and if you just take that data, this is based on his actual data, it looks something like this. It's kind of all over the place. You've got a whole bunch of readings of different charges, and you might say, well, what can we possibly do with that? Well, at the time, people didn't know if the charge was what they called granular, or if it was sort of fluid. Does it come in pieces, or can you have any amount of it? Is it divisible into quantifiable pieces or not? So Millikan's results were very, very good, and he had a whole bunch of them. Remember, there was thousands. I only have 20 or so here. And what he did was he basically, first of all, put them in order. So you here I haven't plotted all the droplet values in order, and I've changed my grids to actually match the pattern that he noticed. He noticed that it went up in a roughly regular amount. It's about 1.6 times 10 to the minus 19, you might know. And on this plot, you can see that we can be on this grid line, or that one, or this one, or the next one. And I haven't rigged the data here. There are some sort of tiny variations, but that's the rough pattern. And instead of going by oil drop number, you can then do something a bit better. If you take all of these numbers and you divide them by the smallest value you've ever found, that's basically calculating how many electrons are on each drop. The charge here, total, and we have the number of charges. So that's that last one here. And his work was quite famous. I think he found every single possible value apart from, I think it was 15. He never found an oil droplet that happened to have exactly 15 electrons on it for whatever reason. Who knows? And you can see there's a directly proportional relationship that goes to the origin. You can see that there's very little deviation. This was the first piece of evidence that the electron had a granular charge. It was a quantized set amount. And not only did he prove it, he also was able to measure it. You can see here the value that comes from this data. It's not exactly the modern one, it's slightly less than that. There was a bit of a discussion at the time, and even some people think that after the experimental result was known, other people were finding the same mistake too. And there's actually a bit of interesting cultural history here, where the people who did the measurements that agreed with Millikan published their results, and the people that got a different value, well, they didn't publish their results. They assumed that they were wrong. And as a result, the scientific community kind of didn't notice this for a little while. It was an example of poor scientific practice where people were more worried about matching known knowledge than actually getting to the bottom of the truth. Here are various example questions to try and give you something for homework. Thank you very much for listening.